Hello friends, today we'll solve the GATE 2023 Digital Electronics problem of Electronics and Communication paper. So this is the first question. It is saying that in the circuit shown below, P and Q are the inputs. The logic function realized by the circuit shown below is, so it's the 2 into 1 mux. Okay, so we know that output expression of a 2 into 1 mux is the select line Q bar into I0 plus Q into I1. Okay, so when select line is 0, then I0 will be passed. When select line is 1, then I1 data will be passed. Okay, so this is the term. Now here I0 is 0 and I1 is P, so this part is 0, so this is QP, so 0 plus QP, QP. So basically it is working as an AND gate. Okay, so Y is equal to PQ. Just for extra information, let's see, a 2 into 1 mux can be used to make NOT and an OR gate. To make NOT gate, what we will do is we will put this as I0 as 1 and I1 as 0, and let's say we need to invert B, then we give this as B, so Z will be B bar I0 plus B I1. So we only want B bar, so this part will be 0 and B bar dot 1 is B bar. Okay, similarly AND gate we have just seen. For OR gate we give A, 1 and B, so this will be like B bar I0 plus B dot 1, so this will be like B plus A. Okay, using this normal Boolean algebra law that x plus x bar y is x plus y and x bar plus xy is like x bar plus y. So whatever which is separate will become and the other function will come. Like here separate part is x, so x will come. Here x bar is separate, so x bar will come. Now the extra function is y, so y will come. But for NAND or NOR or XOR or XNOR, we need a NOT gate also. NOT gate means we need one more mux also. Okay, so you can think of these in backward way. Like suppose you want to implement XOR gate, okay, using a 2 into 1 mux. So we know that 2 into 1 mux means Z is equal to it will be like B bar I0 plus B I1. Okay, now we want A XOR B, which is B bar A plus B A bar. So in terms of I0 we will give A, and in terms of I1 we will give A bar, so like that. So 1 mux for NOT gate, 1 mux for this, so 2 into 1 mux will be required to make XOR gate or NOR gate or NAND gate or XNOR gate, as you can see here. So you can think backward also and make the appropriate inputs. Okay, so this was the first question. Second question was like a synchronous sequential circuit shown below works at a clock frequency 1 gigahertz. The throughput in megabits per second and the latency in nanosecond respectively are. So latency is nothing but like total delay from input to output. Okay, so normal propagation delay. So if your bit is here, then it will take like 1 nanosecond to come here, 1 nanosecond to come here, and 1 nanosecond to come here. So total each bit will take 3 nanoseconds to come from input to output. Okay, so it's a serial in serial out kind of circuit, shift register. Okay, so this will be 3 nanosecond, and this new word is throughput. So throughput is what? Throughput of a sequential circuit is number of bit coming out at output per second. तो हर सेकंड कितने बिट आउटपुट पे आ रहे हैं, that is throughput. Now here we can say that after every 1 nanosecond 1 bit will appear at output, because this bit will come here at 1 nanosecond and again previous bit will also come. So after every 1 nanosecond 1 bit will come here. Okay, so you can say that in 1 second 10 raised to power 9 bits will come. Okay, so 10 raised to power 9 bits will come here at every second, so which can be written as 10 raised to power 3 into 10 raised to power 6, so which is 1000 megabits per second is the throughput of this circuit. Okay, so this 3 is right, so that's why I ticked it, but only this part is wrong, so all these are incorrect. Okay, so frequency is 1 gigahertz, so time period is 1 upon frequency, so which is 10 raised to power minus 1 second, so 1 nanosecond. So time period is 1 nanosecond, So total this is 3 nanosecond. Okay. Okay. So clock frequency we have found out is 1 nanosecond. So after every 1 nanosecond, one bit will move. So this is 3 nanosecond, and therefore latency is 3 nanosecond, and throughput is number of bits will come is like after every 1 nanosecond one bit will come. So in 1 second 10 to the power 9 bits will come, so it is 1000 into 10 to the power 6, so 1000 megabits per second is the throughput. Okay. Third question is on resolution. SNR of an ADC. It is saying that the signal to noise ratio of an ADC with full scale sinusoidal input is given to be 61.96 dB. Resolution of the ADC is, so n is also called as resolution or effective number of bits of the ADC, or number of bits of the ADC, different names, and this formula has been asked multiple times in GATE exam. So SNR of an ADC is given to be 61.96 dB, and this we know is equal to 1.76 plus 6.02 n. Okay, so we'll simply solve for n. So n is equal to 61.96 minus 1.76 divided by 6.02, so which is 60.20 divided by 6.02. Okay, so this simply gives us n is equal to 10. Alright, so number of bit of the ADC or resolution of the ADC is 10 bits. So again, very easy question. This question is on propagation delay. For the circuit shown below, the propagation delay of each NAND gate is 1 nanosecond. So the critical path delay in nanosecond is, so critical path is like worst case delay, maximum delay. Okay, so you can see that this here input will go first here after 1 nanosecond, then it will come here, and then it will take 1 more nanosecond to come out. Okay, similarly if there is some input at B, then it will go after 1 nanosecond here, then it will go here, and then after 1 nanosecond it will, after multiplying with this, it will come out. So no matter whether it's go here like this or like here like this, though after like maximum of 2 nanosecond both output will be 100% stable. So we can say that the critical path delay of the circuit is 2 nanosecond. Okay, again easy question. Fifth question is like on synchronous counter type. For the given sequential circuit, initial state are Q1 is equal to 1, Q2 equal to 0. So for the clock frequency 1 megahertz, the frequency of signal Q2 in kilohertz is. So for all such we make the table. Okay, and we'll solve it using table. So you can see that we make the table is a D flip flop. So D flip flop means next state is present D input. So present state flip flop input next state. So present state is like you can see it is Q1 Q2. So we write it as Q1 Q2, and initial was given to be 1 0. Now D input, this D1 input is what? This is connected to Q2. Okay, and this D2 input is connected to Q1. Okay, so this is 1 and this is 2. Okay, so next state will be D input only of D1 input, and Q2 bar will be D2 input. Now this is 1 0, so 1 0 will be D1 is equal to Q2, so this is 0, and D2 is equal to Q1 bar, so this is also 0. So next state will be also 0, because next state is D input only, so Q1 plus is 0 and Q2 plus is also 0. Now this 0 0 will come here. So now you can see that Q2 D1 is Q2, so Q2 is 0, and D2 is Q1 bar, so this is 1, so 0 1. So next state will be also 0 and 1. Okay, now this 0 1 will be this 0 1, so this is D1 is Q2, so Q2 is 1, and D2 is Q1 bar, so Q1 bar is 1, so 1 1. So next state will be also 1 1, so Q1 plus is D1, so D1 is 1, and Q2 plus is D2 input, so this is also 1. Okay, so 1 1. Now 1 1 will come here, then it is D1 is Q2, so Q2 is 1, and Q2 d2 is q1 bar, so this is 0, so 1 0, so next state will be 1, so again we are getting 1 0, and so on. This thing will repeat. So now the question is asking us about the frequency of signal q2. Okay, so you can see that q2 signal is like this. It is like 0 0, then 1 1, then again it is going at 0 0 1 1, so it is repeating after like 4 clocks. Okay, so after first clock it is coming here, then second clock, then third clock, then fourth clock. So after 4 clock it is coming to initial position. Okay, so q2 signal repeat itself after every 4 clock pulses. Okay, so the frequency of signal of q2 in kilohertz is f clock by 4. Okay, which is 1 megahertz by 4. So which is, now we want the answer in kilohertz, so we'll write it 1000 kilohertz by 4, so 250 kilohertz is the correct answer for this question. So 250 kilohertz is the correct answer. So these were the all 5 questions, all look pretty easy. Okay, so thank you.